Hello and welcome to today's Nexperia Quick Learning video. In this session we'll be talking about how to reduce the number of MOSFETs in parallel through using Nexperia's CCPAK1212 MOSFET package. But first, why are MOSFETs used in parallel? Well, in today's automotive and industrial applications, more and more power is being demanded from them all the time. These include applications such as electric vehicle and light electric vehicle inverters, brushless DC motors, DC to DC converters, power switches, and battery management systems. The power in these applications can reach several kilowatts, which can exceed the maximum operating temperature for a single standalone silicon MOSFET. Therefore, multiple devices are needed in parallel in order to handle the huge amounts of current and prevent such a large increase in temperature during operation. However, there are some disadvantages when it comes to MOSFETs in parallel. The first is the unequal current sharing caused by RDS on spread, and unequal switching times caused by VGS threshold and QG spread. And these are things that affect all power MOSFETs and is due to the tolerances in the silicon production process. The second, and arguably more significant, is the additional bill of materials, cost, and PCB space required for the application. These three aspects are things that a designer would like to minimize as much as possible when coming up with their new design. So how can MOSFETs in parallel be reduced without compromising the overall thermal performance of an application? In our case study, we have MOSFETs being used as load switches in a high power 48 volt application, required to handle a 50 amp load current continuously at an elevated ambient temperature of 120 degrees C. So let's see how Nexperia's CCPAK1212 1 milliohm 100 volt part fares against another 100 volt 3.5 milliohm D2PAK market alternative through thermal simulations. For elevated temperature operation, we used RDS on values for both devices at 150 degrees C, allowing us to calculate realistic I²R conduction losses per package. At this temperature, the total resistance of the two parallel CCPAKs is near identical to the 6 parallel D2PAKs. Assuming equal current sharing between devices, for 50 amps total, each CCPAK will conduct 25 amps, whilst each D2PAK conducts 8.33 amps. These power losses were then fed into each device in the CFD simulation. For a realistic PCB setup, we've used a 70 by 50 mm, 1.6 mm thick 2-layer FR4 PCB resting on a 3 mm thick aluminium plate of the same area. However, the PCB plate will be separated with a 1 mm thick thermal interface material with thermal conductivity of 5 watts per meter Kelvin. For stack up, the top copper plane is the recommended solder footprint with no additional traces, with 1 mm spacing between devices, whilst the bottom plane is a complete copper pour, as the ground is in both cases connected at the top and bottom with thermal wires for improved dissipation. Finally, drain and source nets were electrically isolated, shown by the blue border area. After the simulations were complete, we see that CCPAK1212 achieved comparable junction temperature and equivalent PCB temperature rise, whilst reducing the space by 68% compared to D2PAKs in parallel. This thermal performance is achieved due to the large silicon die and large copper clip lead frame offered by the CCPAK1212 package. To summarise, Nexperia's CCPAK1212 aims to meet the thermal demands of next generation high power automotive and industrial applications. This has been demonstrated by its ability to reduce the number of MOSFETs in parallel, as shown in our case study, without compromising thermal performance overall. Our case study is not limited to just D2PAKs, but can be applied to reducing other MOSFETs in parallel, such as 5x6, 8x8 mm and Toll packages. Thanks for watching. For more information about our MOSFETs, please visit our website at nexperia.com/MOSFETs.